Hello, everybody. All right, with our intro out of the way, we are going to now be able to actually talk about quantum numbers. I mentioned in class a little bit, so if you didn't have me in class, or if I didn't say it on the day you were here, this first chapter is going to be the most content heavy. I am just going to be pelting you with material. There is a ton that you're going to have to learn. After this is going to slow down quite a bit, and there's going to be more specific things that we'll work on as we go through. But this chapter, just by its nature, I just got a whole bunch of concepts I got to cram into your brain so you can really be able to understand what we're talking about in the later parts of it. Quantum numbers aren't super important, but I think the state of Missouri requires me to teach them to you, and this is the best place to do it, and it will help explain a little bit about the bonding stuff we're going to get to later. So Erwin Schrödinger is the Austrian physicist who developed the equations that gave us the quantum mechanical model of the atom. Quantum theory basically says electrons have some kind of energy level, an orbital, an orientation, and a spin. And that's what quantum numbers are there for. This is kind of came out of the ideas of the wave-particle model of the electron. I've actually decided, based on what I've been looking at, I'm going to touch on that more in chemistry starting this year. So those of you who had me for chemistry don't really know about this. But the general idea is that for a long time we weren't quite sure how electrons functioned. They are definitely the weirdest of all of the particles in the atom. And for a long time we thought it was a particle, and then we thought it was a wave, and then we kept realizing there was problems with both of those things, and then thanks to Einstein doing the same idea with light, where he was working with light, he realized that light existed as both a particle and a wave. It has photons, but it also has a wave frequency, and because of that, light exists as an electromagnetic form of radiation, and it has different wavelengths of light, but it also does have specific individual particles that can carry energy. Schrödinger expanded upon this and the ideas that he was working with, and basically came up with the idea of quantum mechanics. Now, you probably recognize Schrödinger's name. I don't remember if I put this in the later slides. You're probably thinking of Schrödinger's cat and the idea that, you can put something in a box and you won't know if the cat is alive or dead. The specific experiment that he was dealing with involved him having basically one single radioactive particle bouncing around inside of a box. And there was a detector in that box that if it detected the particle, if that particle passed in front of it, it would then break a vial of poison and kill the cat that was inside of it. And until you opened it, you had absolutely no way of knowing whether or not that particle had been detected and whether or not the vial had been broken, and therefore you had to assume that the cat was both alive and dead. What most people don't realize is that he was stating this idea to describe how absolutely bonkers absurd quantum mechanics was. He was not saying, oh yes, this is the nature of the world. He was saying, it's like we have to assume the cat is alive and dead. That's so crazy. That's absolutely ridiculous. Why would that ever be a thing? A cat's not both alive and dead. But the more and more he researched, he kept realizing that seemed to be kind of the case, where a lot of the stuff in quantum mechanics feels like it doesn't make sense, but it's how it seems to work. Thanks to his work, though, we got to come up with quantum numbers, and these are how we describe locations of electrons. In general, they describe distance from the nucleus, shape of an orbital, orbital's position, and then the spin of an electron. It's early in the morning. I apologize. Get some hydration in me. So let's consider the following. Now, we're going to kind of treat quantum numbers are kind of like an address in a way. So we're going to get a little bit gender normative here, so I apologize for any of my gender fluid people in my audience, but this is purely because it makes the example easier. This is not to hide anyone with unique gender identities. But if we look, we've got Mr. Diamond, 211 Northeast Revere Avenue, Bend, Oregon, 97701. Every value tells you a piece of location. You have a title, which can be one of two things. Again, we're being gender normative here. I apologize for that. You have a name, a location broadly speaking, and a specific location. This is similar to the quantum numbers. The first thing that you need to know is, okay, where is it located broadly speaking? And we don't write our addresses in this order, but if you think about it, the things that you need to know specifically would be in order. Where are you located, state, city-wise? Where are you located within that location? Who are you, or what household are you a part of, and what specific title do you hold in that household? And so the distance from the nucleus is like the location, broadly speaking. It's like saying Bend, Oregon, and giving the zip code. And then, okay, we're in Bend, Oregon, but now we need to know specifically where or what position in there. That's like your street address. And then to know which specific people or person you're looking for in there, you can get a last name, and then you got a Mr. or a Mrs. You've got 2 possible spins. Again, gender normativity. I apologize for that, just for the example being convenient here. Spin of electrons can be one of 2 things. So our first principal quantum number, or our first quantum number, is the principal quantum number, aka N. This is basically your city-state address. It describes the main energy level or shell of an electron. As it increases, the distance from the nucleus increases. Values of N are all positive integers. They range from 1 to 7. It's basically, if you remember the orbital levels we worked on, it's the first number when you did an electron configuration. So 1s2, which would be describing helium's electron, the electron that would be placed finally on helium. 1 is the principal energy level. And so you can also remember there's 7 of them, because I don't have another one close by, so we're going to, I think there's one at the back of this book. This is what you get for having Diamond unprepared. Bam. So this is quite awkward. I hope I'm in frame. I don't know if since this was like my second video, I didn't say it in my first video. I cannot physically see while I'm at school what my camera looks like, so I really hope this is in frame. First energy level would be here, second, third, fourth, fifth, sixth, seventh, but you have to remember that the different subshells start on different energy levels. So S starts on 1, P starts on 2. Even though it's in the 4th row, D starts on 3. And even though it's in the 5th row, F starts on 4. Actually, it's in like the 6th row, right? Yeah, 1, 2, 3, 4, 5, 6th row. It starts on 4. So those numbers, those first numbers, are telling you what shell, what layer, basically, are you looking at. The second quantum number is the angular momentum quantum number, aka cursive L, is what's used to describe it. It describes the sublevel and the shape of it. It can be a first sublevel is an S shape. That's the first one that gets made. It's just the sphere. It contains 1 orbital. The second sublevel is P. That's the dumbbell shaped one. That contains 3. Third is D, double dumbbell, contains 5. And then F is the 4th one, flower or fancy shaped, contains 7 orbitals. This is the order that they could be added to it. Now, we're not going to actually use numbers to assign them, but I will at the end of this explain how the number will actually work for it. The third quantum number is the magnetic quantum number. That's M. This describes the orientation in space. So if you remember the electron box notation, which is everybody's least favorite one of them, in a S orbital, there was 1 box, and so the magnetic quantum number would just be 0. It's just whatever that 1 box is. But P orbitals, there are 3 possible options. So your second quantum number, if it tells you it is a P orbital, you then have to say, okay, well, my third quantum number will tell me which of these 3 boxes does it go in. You'll notice that it goes from -1, 0 to 1. I have no idea. I was not at the council that decided it was going to go negative to positive, and how they were going to do this. And then all the way down to F orbitals. We'll skip over D because it's the same idea. F orbitals can have 7 of them. So you could say it's on the 5th energy level. It is an F orbital, and it is in the -1 location. It is in the, again, I point to the screen. It is in the -1 location. So that has now narrowed it from big energy level, what shape is it, which specific orbital are we talking about? And then the final quantum number is spin. That's why I said it was like the Mr. or Mrs. Again, gender normativity. I apologize. I'm sure some of you are tired of me saying that, but just for the purpose of this example, not to knock any gender fluid people in this. So it's basically just describing the movement of an electron in its orbital. It's either going clockwise or counterclockwise. Or as we drew it with the arrows, it's either an upspin or a downspin. And this is basically how the 2 electrons can exist within one shell and not be just like repelled completely away from each other. They're basically moving in such a way, again, I know they don't work in actual patterns, but they're moving in such a way that they never really interact with each other. They're going opposite directions, they're doing opposite things. So to go back here to the beginning, the first quantum number ranges from 1 to 7. The second quantum number will then range from whatever number you had minus 1, I think. if I'm remembering correctly. Again, we're not actually going to work with the numbers. So for example, if it's on energy level n equals 2, you would start with your options are either 1 or 0. 0 being S, 1 is P, 2 is D, 3 is F. Again, I know this is like a really weird, and you're not going to have to use this. This is just for those of you that want to know. And then to figure out your magnetic quantum number range, you take whatever number you have, and you go from positive that number to negative that number. S is 0, so positive 0 to negative 0 is just 0. P, positive 1 to negative 1, 3 options. D, positive 2 to negative 2, 5 options. F, positive 3 to negative 3, 7 options. And then you just do for spin plus 1/2 for an up spin, minus 1/2 for a down spin. That's how you identify it. So I'll work out one quick example, I guess. I'm going to get a piece of paper out in front of me. So let's take, for example, we'll do aluminum, Al, which has 13 electrons in it. Al has its last electron put in 3p1. 3p1 is the final electron that's put there. So its quantum number, its address for that electron would be 3, because that's its energy level. P is represented by a 1. It's in the first slot, and so it went from -1, 0, 1. So it would be 1, -1, and then it's the first one added, so it's plus 1/2. So the address of aluminum would be 3, 1, -1 plus 1/2. And you can see why we're not actually really going to work with this that much, because first of all, it's not entirely relevant to what we're doing in this class. It's just a chemistry concept I have to make sure I've taught you at some point. But that is how it works. It gets a little bit vague, and it's a little bit hard to understand, especially when you get really deep into the actual periodic table. It can be kind of frustrating to figure out what's going on. But that's how quantum numbers work. If you have any questions, let me know. I will ask you questions about what the 4 of them are on a test, but I will not ask you to make a quantum number, like write down what the quantum numbers for an electron are for the actual main part of the test. It might be a bonus question. No promises there. Again, if you have questions, send me an email, leave a comment to this video. Otherwise, I hope you have a great rest of your day. I hope to hear from you soon, and good luck, everybody.